Hi, my name's Kayleigh, and I will be presenting on the paper Detecting AI Planning Modeling Mistakes, Potential Errors, and Benchmark Domains on behalf of myself and my co-author Pascal Bercher. So a bit of background, AI planning is an area of AI concerned with using algorithms to generate sequences of actions which will transform some given initial state into a desired goal state. Unlike more commonly used forms of AI like machine learning or large language models, AI planning is not reliant on probabilities or large sets of training data, which makes it particularly suitable for applications which require a more deterministic and traceable form of AI. One of my favorite explanations that I've heard for why AI planning is helpful is that you wouldn't want ChatGPT flying your plane. AI planning is used in a variety of applications in industry at the moment, including transportation problems, particularly with autonomous vehicles, chemical reaction simulations, robotics, urban planning, scheduling, and manufacturing. And traditionally, when it's used in these cases, it's used in a domain-specific way. So that means somebody is required with a deep knowledge and expertise of these algorithms to write them tailor-made for the use case. And this is an expensive, inefficient, and limited way of doing things because there are not that many people with enough expertise in this niche for that. In the past 10 to 15 years, there have been some significant breakthroughs made in research into developing domain-independent planners. And these are planners which have the algorithms standardized to be used on any planning problem. So all you need to solve any planning problem with a domain-independent planner is to provide the planner with information about the planning problem and the world in which it exists through what we call a problem file and a domain file. So the domain files encode all of the possible actions that can be taken in the world of the planning problem and the preconditions that are required to be true for each action to be undertaken and the effects of that action on the state of the world. And the problem file provides an initial state of the world and a desired state that we want the planner to get to. And what a domain-independent planner will do is it will take a domain file and a problem file, and it will generate all of the possible sequences of actions which can be used to transform the state from the initial to the goal state. This is much more flexible and easy to use for a wide range of users because the syntax for these domain and problem files is much less complex to pick up than the planning algorithms themselves. However, the key word here is if you have a correct domain, then the domain-independent planner can solve any planning problem. And this is tricky because domain creation is a hard and long process. You have to take all of the relevant facts about a world and include it in a way that the planner can understand. And it's the only phase of the domain-independent planning process which requires user input, which means it is also the most error-prone phase. In addition, because these domain-independent planners are relatively new, the syntax that we use to encode the domain and problem files is still being developed and is very new, and therefore the software surrounding this syntax has very underdeveloped error diagnosis capabilities. And this is a problem for two reasons. Firstly, say that I have a domain file that has 1,000 lines of syntax and I miss a semicolon on one line. I want the parser of the planner or a domain modeling assistance tool to be able to point me to that problem so that I can fix it really quickly. But at the moment, not all of the software surrounding these syntaxes can do that kind of thing reliably. And so instead, you might find yourself searching through every single line of code trying to find that missing semicolon. The second problem is even worse, which would be that it's possible at the moment for certain errors to make a mistake in a domain file and feed it to a planner, and the planner won't even notice that the domain file is incorrect. And will still complete the planning process, which means it's either going to give you incorrect solutions or it's going to tell you that no solutions exist when they actually do. And this is a huge problem. Unfortunately, the researchers who have the depth of knowledge and experience to be pioneering AI planning don't have a lot of time left over to think about domain error diagnosis. But luckily, I do, and over a period of 6 months at the start of the year, me and my co-author Pascal Bercher compiled a list of potential domain errors that could be made in this domain creation process, which we divided into two categories. So the first category is syntax errors. These are very clear transgressions of the syntax that should prevent a planner from running on a certain domain. And the second was potential semantics errors. And these are not necessarily errors, but they are red flags that there might be something wrong with the meaning of the syntax and that the modeler should go back and check that that's what they want to say. And we suggest that planner parsers or domain modeling assistance tools are able to flag these potential semantics errors as warnings. Once we had this list of potential domain errors, we translated it into a benchmark repository of flawed domains. We did this for both classical and hierarchical planning. Hierarchical planning is just an extension of classical planning where in order to generate the sequence of actions in a solution, we take large compound tasks and we break them down into a series of small atomic tasks. So for classical planning, we wrote a repository for each error or potential error in the, not a repository, we wrote a domain containing each error or potential error in the language, in the planning domain definition language PDDL, which is very commonly used in this area. And for hierarchical planning, we used the hierarchical domain definition language HDDL, which is a much newer syntax. This benchmark repository is publicly available on GitHub, and we hope that other researchers or users of this syntax will help to improve it, to extend the current domains that we have, and to add any examples of errors or potential errors that we may have missed. This repository is intended to be used by the developers of domain modeling assistance tools or planner parsers to ensure that they are picking up all of the necessary errors. And as far as we're aware, it is the only existing benchmark repository for this purpose. Once we completed this repository, we used it to perform an evaluation of currently used domain modeling assistance software and planner parsers, and I'll take you through a couple of examples of the results that we got from that. So the most commonly used planner that we tested was planning.domains. This is a cloud-based planner that's very widely used as an educational tool for AI planning. We found that it picked up 79% of the syntax errors that we fed it. And we weren't just testing, do these tools pick up the errors, but also do they guide the modeler to fixing the errors? So do they provide a helpful indication of the location of the error? And do they provide a clear and helpful error message? And we found that of the errors it picked up, planning.domains provided location guidance 64% of the time and provided helpful error messages 55% of the time. The best tool that we tested was the VS Code plugin, which provides syntax support for PDDL domain modeling, and which is integrated with the planning.domains planner on the back end. This plugin picked up 100% of the syntax errors that we fed it. It provided location guidance 75% of the time and a helpful error description 42% of the time. We also found it was the only tool that was able to pick up any potential semantics errors. None of the other tools picked up any semantics errors. The VS Code plugin was able to detect unused predicates. The most advanced hierarchical planner that we tested was Panda, and this picked up 68% of the syntax errors we fed it, but because hierarchical planning is an extension of and subsumes classical planning, there is actually a wider range of errors that we were testing for the hierarchical planners. So of the tests that we ran on both hierarchical and non-hierarchical planners or modeling tools, Panda picked up 86% of those, which made it the second best tool for error detection. It provided location guidance 93% of the time and helpful error messages 53% of the time. So I won't take you through all of the results for all of the tools that we tested. There are more in the paper. I'm not going to give spoilers for everything. But what we concluded overall was that more robust error checking is required for all of these tools. On average, there was a detection rate of only 65% of syntax errors. So that means there could be a lot of flawed domains being fed into these tools without anybody noticing. And we found that there was almost no detection of potential semantics errors, except for that one potential error that was picked up by the VS Code plugin. So there's a huge room for improvement there. As well as improved error detection being required, we also found that more helpful error diagnosis is required to help guide an inexperienced modeler to being able to solve their error. So on average, we found that of the errors picked up, 78% of them came with helpful location guidance, but only about 48% of them came with a clear and helpful error message. The future work resulting from this is, first and foremost, it would be great to have the parser code of these tools improved to catch more of these undetected errors. The developers of the Panda Planner have actually already fixed 3 of the errors that we found in their software. The passes could also be improved to provide more helpful error descriptions when they do pick up some of these errors. In terms of our repository, we would like to improve the test domains to make them more concise, and we're hoping that other researchers will help to add any examples of errors that we may have missed. We think that it would be really helpful to have a cloud-based hierarchical planner. When we were testing, we found that there was a huge difference in accessibility between the cloud-based planning.domains classical planner and all of the hierarchical planners, which required quite a complicated and error-prone software download process. We would also like to repeat this to create a repository of potential errors in problem files. The scope of our project was limited to just potential domain errors, but problem files are just as important to the domain-independent planning process, and we'll also need to be able to pick up errors in those problem files if domain-independent planning is going to be used widespread in industry. Finally, a few acknowledgements, first to my co-author Pascal Bercher, and also to a bunch of different academics and researchers who helped us along the way in compiling a comprehensive list of errors and potential errors and a helpful benchmark repository. Particular thank you to Bernd Schattenberg for the conversations that we had with him. Okay, I will finish up and pass over to you for questions.